Welcome to The Explainer. Today, we are going to tackle one of the biggest mysteries in the entire universe. I'm talking about that invisible force, the one that literally keeps your feet planted on the ground and, at the same time, holds the moon up in the sky. So, what does a falling apple have in common with the moon? It sounds like a riddle, right? Well, this simple question, famously puzzled over by Sir Isaac Newton, kicked off a complete revolution in how we see the cosmos. All right, so let's get into it. The story, or at least the legend, begins in a pretty ordinary place, an English garden. So Newton's sitting there and he sees this apple fall. And he starts wondering, why does it fall straight down? Why not sideways? Or heck, why not up? He figured there must be some kind of invisible pull, an attractive force coming from the Earth itself. And since apples fall straight down no matter where you are on the globe, that pull has to be aimed right at the center of the planet. But here's where it gets really interesting. He thought, okay, this force pulls on an apple. But could it be the exact same force that reaches all the way out into space and keeps the moon from just flying away? I mean, that was the big mystery, right? Is this a local thing or is it universal? Now, before Newton could crack this cosmic case wide open, he needed some clues. He wasn't starting from scratch, and luckily for him, those clues came from the absolutely groundbreaking work of another brilliant mind, an astronomer named Johannes Kepler, who had spent years just meticulously mapping the heavens. Okay, so clue number one from Kepler was a real shocker at the time. For centuries, everyone just assumed planets moved in perfect circles. But Kepler proved that's wrong. Their orbits are actually ellipses, basically kind of stretched out circles or ovals. And the sun isn't at the center, it's off to one side at one of these things called foci. Then there's his second law. It says a line connecting a planet to the sun sweeps out equal areas in equal amounts of time. Now I know, that sounds a little technical, but what it means is incredible. It means that planets actually change their speed. They zip along faster when they're close to the sun, and then they slow right down as they swing farther away. It's like a cosmic dance. And his third law? Yeah, it looks a bit math-heavy, I know. But the takeaway is this. It showed there's a beautiful, predictable relationship between how long a planet's year is and how far away it is from the sun. So think about it. Kepler gave us the how. He laid out the exact rules for planetary motion. But he couldn't explain the why. And that's where Newton steps back into the picture. All right, so how on earth did Newton connect these grand cosmic rules with a simple apple falling from a tree? Well, it took a massive leap of imagination, a real stroke of genius. Let's try a little thought experiment. Imagine you're spinning a stone tied to a string around your head. What keeps it from flying away? The string, right? It's constantly pulling the stone toward the center. That pull is called centripetal force. And Newton had this epiphany. What if there's an invisible string connecting the Earth and the moon? Something that's always pulling the moon inward, stopping it from just shooting off in a straight line into deep space. And just like that, he connected all the dots. The moon, he realized, is constantly falling toward the Earth. But because it's also moving sideways really fast, it just keeps missing. It's in a perpetual state of falling around us. And the force causing that fall, that invisible string, he proposed it was the very same force that pulled the apple to the ground, gravity. Not just on Earth, but stretching all the way out into the cosmos. This realization, this was huge. It led to one of the most powerful and important moments in the entire history of science. Newton managed to capture this universal idea in a single, beautiful, elegant equation that would basically run physics for the next few hundred years. And there it is, the universal law of gravitation. It looks simple, but its meaning is profound. It says that every single object in the universe, you, me, this planet, a distant star, attracts every other object with a force you can actually calculate. So let's break this down real quick. The force, F, depends on the masses of the two objects. The more massive they are, the stronger the pull. And it depends on the distance between them. This is super important. As things get farther apart, the force gets weaker. A lot weaker, actually. If you double the distance, the gravitational pull drops to just 1/4 of what it was. This law also clears up something people get mixed up all the time. Mass versus weight. See, your mass is the amount of stuff you're made of. That doesn't change, whether you're on Earth or Jupiter. Your weight, though, that's just the measure of gravity's pull on your mass. So yeah, you'd weigh a whole lot less on the moon. Not because you've changed, but because the moon's gravitational pull is so much weaker. So have you ever wondered why you don't just, float over and stick to the person sitting next to you? Well, look at this number. That's the gravitational force between two regular-sized adults sitting a meter apart. It is tiny, absolutely minuscule, which is why we don't feel it in our everyday lives. Gravity really only becomes a major player when you're dealing with massive planet-sized objects. Okay, so if gravity is this universal force always pulling on us from everywhere, what does it take to fight back? What does it take to actually escape its pull? Well, take a look at this chart. As you go higher and higher, the pull of Earth's gravity, what we call G, it definitely gets weaker. But here's the crazy part. Look at that communication satellite, way out there. There's still gravity. It never truly goes to zero. In theory, Earth's gravity reaches out across the entire universe. It just gets infinitely weaker the farther you go. But there is a way out. There's a magic number, a specific speed you need to hit. If you can go fast enough, you can break free from a planet's gravitational grip for good. You won't fall back down. You'll just keep going. And for our planet Earth, that speed is 11.2 kilometers per second. To put that in perspective, that's about 40,000 kilometers per hour. That's the speed a rocket has to hit to escape Earth's gravity and head out into the solar system. For more than 200 years, Newton's law was it. It was the absolute, definitive answer on gravity. But science never stops, does it? It always pushes, always asks deeper questions. Which brings us to a whole new way of thinking about this. So Newton saw gravity as a force, right? An invisible pull. But what if it isn't a force at all? What if massive objects are literally bending and warping the fabric of space and time, and what we feel as gravity is just us moving along those curves? Now, that mind-bending idea, well, that's a story for another explainer. Thanks for joining us.